This is a summary of the factors affecting intermolecular forces of attraction for simple molecules. Basically, there are three factors, alright, and we will go in the order of 1, 2, and 3. Okay, so if 1 cannot explain the physical properties, then you move on to 2. If 2 cannot explain the physical properties, then you move to 3. Number 1 is the nature of the intermolecular forces of attraction. There are three types of intermolecular forces of attraction: dispersion forces, dipole-dipole interaction, and hydrogen bonding. From your lecture, okay, just a quick revision. Dispersion forces is basically due to the unequal distribution of charge, alright, randomly. So for example, okay, randomly molecule A may have a free movement of electrons in the molecule. So the electrons, okay, may tend to go to the left side, resulting in a delta minus, and on the right side a delta plus. Alright, so this is a temporary dipole, okay, and it will induce a dipole with the neighboring molecule. Okay, so here delta plus will induce delta minus on the right side, and so on. So at every single moment, it's able to induce various dipoles. Alright, and in the next moment, all these dipoles may change. So another name for dispersion forces is basically induced dipole interactions. Now, molecules can be divided into two categories: the polar molecules and the non-polar molecules. We all know that for non-polar molecules, the main intermolecular forces of attraction would be dispersion forces. For polar molecules, alright, in the polar molecules, there are electrons as well. So actually dispersion forces also exist. However, in polar molecules, the main intermolecular forces of attraction is either dipole-dipole interaction or hydrogen bonding. Now, hydrogen bonding is for a special category group of molecules. Alright, they usually are have hydrogen attached to a highly electronegative atom, which is F, O, or N. This results in a very, very polar bond. In fact, hydrogen bond is a special case of a dipole-dipole interaction. Now, let's quickly revise. Okay, in what situation will there be a hydrogen bond? Basically, there are two factors. Okay, let's use HF as an example. Okay, the first criteria is that the hydrogen involved in hydrogen bonding must be attached to the highly electronegative atom, F, O, or N. Alright, and this hydrogen undergoes hydrogen bonding with the lone pair on a highly electronegative atom as well. In this case, it's F. Alright, so both criteria must be satisfied. Okay, the lone pair on a highly electronegative atom and a hydrogen attached to a highly electronegative atom. The comparison of these three types of intermolecular forces are as follows. Hydrogen bonding is stronger than dipole-dipole interaction, stronger than dispersion forces. So, for first criteria, okay, basically you are comparing the strength of the various intermolecular forces of attraction and see whether you can explain the physical properties of various simple molecules. Number 2. Alright, if number 1 fails, maybe there is a second factor that you have to consider. That is the number of electrons. As I've stated previously, all molecules with electrons will have dispersion forces. So, even polar molecules can also have dispersion forces. Number of electrons is actually proportional to the strength of the dispersion forces. Alright, so you can compare if more electrons, alright, there'll be a probability of electrons unequally distributed will increase. Alright, so if you compare a molecule with 2 electrons versus one with 30 electrons, you expect the one with 30 electrons to have a greater charge difference, right? And hence greater strength of dispersion forces. Now, the number of electrons can be related to the MR of the molecule. Sometimes we compare by the MR. Okay, so if we know the MR, we would roughly know the number of electrons. Thirdly, is the shape of the molecule. Basically, alright, there is a straight chain versus a branched type of molecule. Usually this is for organic molecules. Now, straight chain molecules usually have higher boiling point than branched molecules. Okay, let's look at one example. Pentane versus 2,2-dimethylpropane. This is the structure of pentane. Alright, it is linear, alright, and straight chain. On the right side, 2,2-dimethylpropane is branched. Now, both molecules are nonpolar, so you expect intermolecular forces of attraction to be dispersion forces. Alright, they have the same molecular formula, so they are actually isomers with the same number of electrons. So this is actually factor 1. We consider the nature. Okay, both have the same nature, right? Both have the same intermolecular force of attraction. Second, right, it will be the number of electrons. Okay, we try to compare and we realize that same number of electrons. So we cannot use these two factors to explain the boiling point, because in reality they still differ slightly in the boiling point. Right, no choice, we move to the third criteria, which is the shape. Alright, so for the straight chain molecule, you realize that the shape, right, is like elongated, while the branch is actually spherical. Okay, so we are comparing these two types of shapes. Now, consider the one that's elongated. Alright, let's say we have a few molecules of the elongated linear pentane. Alright, so if there is dispersion forces, maybe there will be like delta minus here, for example. Alright, of course here will be delta plus. The induced dipoles. Okay, so here will also induce delta plus and delta minus and so on, right? Alright, so these dipoles can interact with each other, alright, via this surface area. Now compare this with the spherical case. Let's say we have 3 molecules as well in the spherical case. Alright, same thing, there will be induced dipole. However, the surface area for interaction becomes very small. Alright, for the spherical case. Hence, we say that for the elongated shape versus the spherical, okay, we can conclude that the linear molecule have higher boiling point. Why? Because there's a greater surface area for electronic interaction, hence leading to greater dispersion forces or stronger dispersion forces and higher boiling point compared to the spherical case.